Thank you. Yeah, this has R, but instead of sports, it's just math. So I hope you'll forgive me. So just a little bit about myself. I did math and statistics at UBC, and since graduating, I worked for about 2.5 years in a small research firm as a statistician. It's actually where Melissa and I met. We worked at the same one, and I did Monte Carlo in my thesis. And so when Melissa said, "Please come talk about R," I thought it's got to be this. I find it's really fun. It translates very abstract math into something a bit more tangible. And so we'll get into it. So first, I'm going to talk about a little bit about some statistical concepts that are relevant. Now, I included a few formulas. You don't really need to pay attention. They're not important for the talk. I just wanted to show you that they're there. Because part of the point is that you don't even have to really do any math. You can just do programmatic solutions to some hard problems. And then we'll get into Monte Carlo, and most of the talk is going to be an extended toy problem where I already know the theoretical answer and R lets you compute it, and then we're going to compare it with our empirical approach. So to start off, you need a little bit about probability. So you talk in statistics about random variables a lot. The idea is that it's some sort of a variable that every time you run an experiment or you sample something has a different outcome. So you could think about flipping a coin, you get tail or heads with 50% probability. And um, that set of outcomes and the associated probabilities, you call that its distribution. And so usually when you're doing statistical analysis, you assume that when you take a bunch of data, it's being sampled from some distribution. So if you look at the entire Canadian population and you poll 1,000 people, every time you poll, you're going to get a new data set, and that's a new sample. So I'm just going to give you a few examples. So binomial distribution, if I wanted to flip 10 coins and see how many coins were heads, you could use that. It's discrete, so each single outcome has a probability. The normal distribution is the most iconic statistics distribution out there. It comes up when you're talking about estimating the averages of things. It's continuous, so the probability of any single value is zero, but I'll show you what that looks like in a bit. And the last example I'll give, which is part of our extended example, is exponential distribution. And I'm going to show you what these look like, but this is often used to model the time between events. So in R, there's a whole bunch of functions. You'll see some of them where you can just sample data. And there's a whole bunch of reasons how it works. And, I'm not an expert in that, but if you just see the examples, it works. It's really easy. And so the idea is that if you have enough data, if you sample enough, you almost have the distribution itself in sort of a data form. And so if you want to figure out properties of your distribution, you can just use the data that you've sampled. And so the whole point is that if you have some math problem you want to solve, instead of doing the math, you can just sample the data, process that data, and then on the other side, you'll have the answer that you're looking for. Um, Now, one term that will come up a bunch, IID, it just means that every experiment you run, it has the same probability distribution, but the outcomes are independent. So if I flip a coin once and twice and thrice, they're all independent. Knowing the outcome of one won't tell you the outcome of the other. So for the first example, I'm going to show you a normal distribution. So most of these examples are going to be the same. So I'll just go through this one in a little bit more detail. At line 11, you can see I'm saying my sample size. I'm going to take 1,000,000 samples from this. In 12, R norm is the function that lets you sample from the normal distribution. So here I'm saying give me n samples with mean 0 and standard deviation 1. And all of the distributions, they have these parameters. You don't really need to worry about them right now. And then in 14 and 15, I'm just picking a grid of points. And then dnorm is that density function. It's the formula that tells you the probability. And so I'm getting it at those grid points. I'm putting it into a data frame. And then in ggplot, I'm making a histogram of those samples. And then I'm adding a geom line for the actual density. And then I'm just doing a few other stylistic things. Now, just to show you, in hindsight, this is really small, so you can't see it. But when I print out that set of samples, it's just a vector of numbers. It's really not complicated. It's just straight up data. And I don't know why this background is it just me or does it look kind of red?
Looks reddish.
Yeah, interesting. Yeah, yeah, yeah. Well, so anyways, so these black bars, so that's histogram of our data that we sampled. It's the same one here. And then that red line is the density function. And so without getting into details, you can see how basically that curve predicts the way the data looks. The second example, it's basically the same, but you can see at line 40 that I'm doing an exponential density, and at line 37, I'm doing REXP. You'll notice a pattern. Every distribution has a term, and you start with either R or D, or there's a few other ones. It looks like this, sure enough. The last example, this is a little different. I just wanted to show you one example of a discrete distribution. Then this is the last one I'm going to talk about it. The only difference really, you can see again, there's R binom at line 59, there's D binom at line 62, and that 64 to 66 business, I'm making this data frame. So because it's a discrete distribution, the data just, I mean, again, I didn't realize it would look so small on the projector. They're just numbers from 0 to 10, right? Each one of them is just a number. And so since there's a finite number of values, I'm just listing how many times did 0 happen, 1 happen, blah, 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 dividing it by the total number of samples, which is 1,000,000. And so that's Y estimate. And then Y true is from that actual function. So that's the actual value. And when I plot it, you get this. So it's a little different. Instead of a curve, you actually get the probability of each of those. And you can see that these last few plots just show you that sure enough, you can sample data and it looks the way that you expect it to. So to get into Monte Carlo methods, the idea is that if you ever want to figure out the value of something, so I'll give you some examples. When you're doing statistics research, there's these quantities like mean squared error, average mean squared error, things like that it's a number that tells you a performance metric. And sometimes knowing how to calculate that is complicated, but you can just collect a whole bunch of data that you've generated and then just push that through a function and it'll spit out an answer that should be approximately correct. And just to give you an idea of kind of the vibe, the law of large numbers, it just says that if you have a bunch of data and you take the sample mean, as you get more and more data, the sample mean, it goes to the true mean. So that's sort of the motivation behind it. So in the extended example, like I mentioned, exponential random variables are used for time between events. One that I think is really cool, if you've ever taken an intro like physics course, half-life decay, they look at radioactive carbon, and based on how much it's decayed, you can carbon date something. And actually, each individual carbon isotope, it takes a certain amount of time to decay, and that actually follows an exponential distribution. That's actually the quantum mechanics. And half-life is just one way of describing what that curve looks like. Another example is that if you look at the concentration of, like if you take a pharmacological drug, the blood concentration apparently is also exponentially distributed. So it's used quite a bit. And there's this parameter, it has a mean. And so this is a very classic, third-year level probability homework problem that you will probably, if you take probability at UBC, you'll probably get this on a homework set. So suppose you want to see how many buses are passing by. The Granville stop on the 99B line at rush hour. Sometimes, I don't know, it's what, 10 minutes if you've ever taken it, something like that? Yeah, something like that. And I feel like this is probably not the right distribution in real life, but again, this is a homework problem. And so you might want to say, okay, well, the time between buses, they're each, I see you smiling. Did you get this in a homework problem? One of the data? No.
Just use the bus.
Oh, yeah, well, there you go. It's thematic. And so if we want there, so if we're saying, all right, the average time is 10 minutes between them, well, then let's just say exponential, that 1/10, you take 1 over 1/10, you get 10 minutes, right? But now a slightly more complicated question. What if I want to look at how long it takes 5 buses to arrive? Now, if you think about it, it's a little bit weird because X1 is measuring the first bus, but the second bus doesn't actually arrive until the first one does. And so the time where, like, not only is there the question of how long does the second bus take to come, but its start point also depends on the first one. So they have a slightly complicated relationship. But surprise, surprise, it's already solved. So if you do a bunch of math, you do a Fourier transform, some other business, you find out that it's something called a gamma distribution. And there's 2 parameters. There's the rate parameter, and then there's the number that you're adding. So this would be 5 and 1/10. And so if you wanted to say, well, on average, how long does it take? 50 minutes. But this is kind of trivial because they're independent. If you want to take the average of them added together, you just add up their averages. So this is kind of pointless. But what we're going to do is we're going to ask slightly more complicated questions that you could also just solve with 30-year probability math. But then we're just going to show that you could actually just use R to solve it instead. So what if I want to know what's the probability that all 5 buses arrive in 20 minutes? Or what amount of time do I have to set so that I'm 99% sure that all buses will arrive by this time? So the first of those two questions, you're just calculating the probability of the distribution of all of them together. The second one, it's a sort of quantile estimation problem. But what I'm going to do, so at line 88 again, here's a million data points. At line 90, what I'm doing, there's this matrix function. So inside I have REXP. I'm sampling 5 endpoints, and that's because I have 5 buses, and for each of those I want n. Their rate is a tenth. And then matrix, it casts like a vector into a matrix. And so when I say n row, I'm saying give me turn this vector into 5 rows. And because everything is all IID, it doesn't matter that they're like the fact that I'm taking one vector of all the samples, it doesn't matter. You could sample 5 different vectors and add them together if you wanted, but it's all the same probabilistically. And then a line 91, I'm adding up the columns. So just to show you what that looks like, I've shown the first 10 columns. So that first column, it looks like what? That's 26 minutes for the first bus to arrive, less than a minute after that one. I've definitely seen them back to back before. 16 minutes, 10 minutes. And then below, I'm adding them all up. So this big S is the sum. So that's the total amount of time it took for 5 buses to arrive. And in the column, and then, yeah, so each column is basically an independent experiment. And there's a million of these experiments. And then as I go on, again, at lines 96 and 97, I'm doing the same thing. I'm picking a grid. I'm getting the actual solution that I know, which is the gamma density. And then I'm making a similar plot. So it looks like this. So this is the arrival time of, all 5 buses, one after the other. Now, this looks like the other plots, but this is actually a bit different because we're not sampling R gamma. We're sampling our REXPs and adding those together. And then we're comparing that to the actual answer that we know from math. And it looks just like the other ones. It's proof that it works. And those two questions I said, they're super, super easy to answer. So the first one, if you remember, it was what's the probability they all arrive within 20 minutes? So if I take that big sum S and I say S lesser than or equal to 20, each one of those is going to be a 0 or a 1, fail or success. It's actually kind of related to the binomial if you think about it, but don't worry about it. And then when I add those up, I'm just counting how many were within 20 minutes, how many experiments within 20 minutes divided by how many experiments. And then in 115, that's just the R solution using P gamma. And then below again for the quantile, I'm just saying, we'll take all those sums and what's the 99th percentile? And then I'm comparing that to the gamma quantile. And so these are the results that I got. So for the 20 minutes one is, so the actual answer is like what, 5.27%, and I estimated 5.3%, pretty close. Granted, very generous sample size. You would never ever get a million samples in an experiment like this in real world. And again, for that quantile, they're both 116 minutes. They're off by less than a minute. So pretty close, but this was a generous sample size. And often when you're doing statistics, you want to figure out, is this statistically significant, right? Because in reality, you wouldn't actually have the real value. So you might not even have something to compare it to. So you'd have no idea if this was good enough. So usually you would call these point estimates, and you want to accompany them with an interval estimate. And so sometimes there's math that you can do to say this is the theoretical one, or you can do some more R sampling approach, and we're going to show both. So I lied, there's more math, surprise, surprise. So the central limit theorem, it's again, probably the most iconic. There's a lot of iconic stats drops in this presentation. This is one of them. So again, you have IID random variables. They all have the same mean and standard deviation. And you want to talk about the average. And so as you have a large enough sample size, the average is normal. On average, it's equal to the real average. And then the spread is sort of the spread of the data, but you're kind of scaling it by the sample size. You estimate the standard deviation from the data. Don't worry about it. R has a function for that. And then there's this thing called a confidence interval. So I'm not going to get into the math, but you can see that basically that 1.96, it comes from the normal distribution. You've got that scaling of your standard deviation by your sample size. And you can see that the interval is centered at your sample mean. I'm just going sample mean, go down by 1.96, blah, 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 and then sample mean up by that same quantity. The interpretation is kind of weird. If you do experiments over and over, 95% of these intervals will contain the true parameter. It's not a 95% probability, but that's kind of outside of the scope. So Yeah, so we already found the estimated probability. So for the first one, right, we're looking at the probability that all five arrive within 20 minutes. So when I summed up s lesser than or equal to 20 and then divided by the number, that's actually just the same as the mean if you think about it. And if I went into the standard deviation, simple enough, just SDNR. And there's that formula that we got from the last slide. And there you go. And what do you know? The true value is in that confidence interval. Sometimes it's not, right? 5% of the time it won't be. But we got lucky here. Um, and so actually, I should probably just take a second here. So the reason why we could use this is because this is a sample mean. In the other example, it wasn't a sample mean. It was a quantile. Now, sometimes the central limit theorem pops up in weird places. Maybe there's some way that you could justify it, but it's not immediately obvious to me. There's an unfortunate typo. I said it is obviously, but it is not obviously applicable. But what we're going to do, so we did that one experiment. In that one experiment, we had a million samples and we got one estimate. So why don't we just repeat that experiment over and over and over and over with new samples of data, and we'll get a whole bunch of estimates. And then let's see, well, what's the 2.7th and the 97.5th percentiles? Because 95% of all of our experiments will be within those two numbers. And I'm going to shoehorn in something about sample size and runtime. So I'm actually going to repeat this experiment. Rather than doing a million sample size, I'm going to do 100, 1,000, and 10,000. And I'm going to see how long it takes to run this experiment because you'll see on the other end a shortcoming of Monte Carlo. So there's a lot here, and it's a lot smaller than I anticipated it would be. But basically, I'm sorry, I wish there was a way to zoom in. Can I do that here? Oh, there you go. That's okay. So if you zoom in, there's still the same point here, right? This is the same before. I'm taking my estimates of the sample size here. N is just going from, it's just iterating through 100, 1,000, 10,000. I'm getting my arrival times. I'm getting the sum of them. And then I'm saying, well, the nth experiment here, I'm taking the quantile, the 99th quantile, and I'm basically saving that. I'm also saving the time at the start of the iteration, and then I'm saving the end time of the iteration. I'm subtracting the reference time up here. So that's how long it took to run this experiment. And then I'm also saving the quantiles that I sampled. And then down here, what I'm doing is I'm going to sample a histogram of these experiments. I'm going to add a red line for the 2.5th percentile, a red line for the 97.5th percentile. And then here again is that actual value that we can compare. And so here it is. So these black histograms, so each one of these samples is one of those point estimates, right? I've repeated the same thing independently. Those red lines are those percentiles. Sure enough, it looks like 95% of the data is within those two red lines. And what do you know? Our theoretical value looks like it's pretty much on the average and probably also the mean of this distribution. So this shows a few things. One, the method makes sense because when you repeat it over and over, on average, it gets it right. And also you can see that our interval estimate contains it quite nicely. So this turned out to be a really accurate experiment. But we also looked at runtime. This is also quite small, I apologize. But basically what I'm doing here, sapply, I'm taking each one of those experiments and then this is running the mean function and the quantile functions because I want to get those red lines, but then also the mean for each of these experiments. And then I'm getting that theoretical value again. And point range, you'll see it makes a point estimate, but also plots the interval. And then this down here is a very simple bar graph that you'll see for the runtime. Oops. So here's the main result. So on the left, well, first let's just look. So on the bottom, you can see there's 100, 1,000, 10,000. Likewise over here. On the left-hand side over here, this is the estimate of that quantile. So just to remind you, this is the number so that there's a 99% chance that all five buses arrive within that time. And then over here, this is the runtime of the experiment. And so the fact that the point estimate gets closer and closer, we got lucky here. That doesn't always happen in this pattern. Sometimes it can go up and down. But on average, you would expect it to be this real line. This is just a coincidence. But what's not a coincidence is that as you increase your sample size, that error bar gets smaller and smaller, which means a couple things. One, you're going to have more statistical power because if you're trying to test something, you're seeing, right, like if there is an effect, then you don't want your interval to contain the actual result. And so if you have smaller error bars, you're more likely to accomplish that. But also just you can see that you have more precise information. But over here, you can see that the runtime grows faster and faster and faster. And so you can see that there's a trade-off where as you increase your sample size, generally speaking, in these kinds of experiments, you get diminishing returns. The increases in your precision get smaller and smaller, but you get huge increases in your runtime. And so there's often a trade-off where, you don't want to use 10 to the 10 to the 10 number of samples because you would never run it. And at some point, it would stop having much benefit. And so sometimes what you'll find in practice is you need to go make your code more efficient. Sometimes there are various like sample size or power calculations you can make. But this is just sort of a central trade-off that you get all the time is runtime and precision versus this over here. And I'll just mention briefly that in the earlier examples, you might remember that we had 1 million. But here, when I do, so that M, the number of experiments I did, um, was 10,000. And then in here, I did, at least in the last case, 10,000 samples. So in the earlier examples, I had 1 million samples. But if you have 10 to the 4 experiments of 10 to the 4 samples, that's 10 to the 8. So that's 100 million. And so if I were to do M 10 to the 6 and N 10 to the 6, both carelessly, I'd have 1 trillion samples, which is going to, in some cases, make it a lot longer to run. If you've ever studied algorithmic complexity, you'll see that's, O of something, something bad, right? And so often, like in my thesis, for example, we were looking at the mean squared error. So if you have an estimator, you know the real value, the mean squared error tells you how accurate that is. But instead of having a fixed answer, you talked about Bayesian statistics. You can also say, well, what if the parameter comes from this other distribution? And so in a lot of statistical studies, you'll get these nested for loops that get really nasty. And so sample size ends up being a big both a pain and a joy. It's both at the same time because then you get to do some cool math and programming, but it is a hurdle that you have to get over. So just to summarize, there's some questions. These ones were fairly easy, but trust me, they can get complicated. If you don't want to do the math, you can do sampling of Monte Carlo in R. It's a little bit more conceptually straightforward, but there's just these practical considerations like sample size and runtime. And when you actually do these I kind of glossed over it. You need to know in principle that it should work. In this case, we knew the answers. Often you don't know the answer. If you have something like you're looking at the average of something, then by the central limit theorem and law of large numbers, you know it's going to work. So that's trustworthy. But otherwise, you need to have some evidence that in principle it should work. And then the other big thing is how do you quantify the error? That ends up being a lot of the work. It's often not very easy. So for example, if you want to estimate the ratio of something, right, you have one confidence interval, the numerator, you have another confidence interval, the denominator. But what if you want to take the ratio of those quantities? That ends up being pretty complicated. And so a lot of the work is just those interval estimates. And that's all.
Any questions?
Maybe this is your next topic, but how did the Monte Carlo results compare if you do it on like a bootstrap sample instead of like natural, like sampling from pockets of human?
Well, so bootstrap sampling, my basic understanding is that if you have a data set and especially if it's small, then you need more sample size. But if you have a data set, in principle, that should look like the distribution that you're pulling from. So the idea is that if you resample, you can get more data. This is a problem where usually you have a specific data set that you want to answer questions about. Usually Monte Carlo is more for answering methodological questions. So rather than having a specific data set and saying, for data sets that look like this, what's a good method? And so since you're specifying what the data sets look like, you're not constrained by bootstrapping. So bootstrapping is more about like a particular data set or problem. This is more about if you want to test out a specific problem. The one exception, again, you mentioned Bayesian. If you've ever heard of MCMC, I always forget, is it Markov chain Monte Carlo or is it Monte Carlo? No, it's definitely Markov chain Monte Carlo. Yeah, yeah. The moment I started saying that out loud, I realized, yeah. That's interesting because usually you do have an actual data set that you're working with. But then when you want to sample from your posterior distribution,
You're generating.
yeah, you're generating. So sometimes, you will have to do Monte Carlo in a case where you're working with a specific data set. But so I'd say that bootstrapping and Monte Carlo like this, they sort of address different kinds of problems or different angles problems. And I think that Monte Carlo would probably be more effective just because you're assuming more information, but then there's a higher risk of model misspecification.
I have a question regarding perhaps out of scope, but for your thesis, what was like the things you were trying to estimate, or what was like the project?
So there's this thing called Bayesian adjustment for confounders where basically so when you do a randomized controlled trial, you balance everything, it cancels out, easy peasy. But if you have observational data, so for example, if you're pulling all records from a hospital, then there could be all sorts of confounders so, if you don't account for age, et cetera, you get problems. But often you don't know which ones you should be included in your models. And if you include too many, you get other kinds of problems. And so there was this method, but the issue is that the way that they did variable selection is it was in the prior. And so your prior would say that, all variables are equally likely. And then in your posterior, it would say, well, actually, no, these sets of variables are what we think are relevant. And sometimes you'd say that we think either it's this set or it's this set. And so you get this weird mixture posterior. And basically what we wanted to do is say, well, what if the data, like nature's prior, is this, and then this is what the investigator picks. So I picked the wrong prior. Well, as a baseline, you say, well, what if I've picked the right prior? Then you would look at basically you look at the mean squared error of you compare, well, what if you specified it correctly? And then you look at the mean squared error of what if you incorrectly specified it. And then so the mean squared error is where you have a particular parameter. So if you have a data set, you assume it's generated from a distribution, right? That distribution has a parameter. But now what if that parameter itself has a prior distribution? And so your mean squared error is when you have a particular parameter. But then when that parameter itself coming from a distribution, if you want to average over that, it becomes an average mean squared error. So it's sort of like an expectation of an expectation. But then when you're comparing two of those, we wanted to look at the percent inflation. And so you have to compare one in the numerator, one in the denominator. And then that would tell you, like, if you have, 100% would mean that it's the same. On average, you're not inflating your error at all. If you have 150% on average across studies, you're having a 50% inflation in your error. So that actually kind of goes back to the point that this is just saying in hypothetical situations, if you misspecify your data in this way, what would that do across studies? And so it's not even about a specific data set. But there's all sorts of statistics research where they'll do Monte Carlo experiments. Sorry, did that answer your question? Yeah.
Any questions?